So, today we are going to discuss the most interesting topic as far as a chemist is concerned. This is the formation of a chemical bond. A chemist is particularly interested in knowing why a chemical bond is formed, and of course, it would be very nice if the chemist can calculate the bond energy and so on, bond length and so on theoretically. And the nice thing is that these days it is very easy to do this kind of calculations. So, the topic of today's discussion is the chemical bond. Now, of course, one may say that H2 molecule is the simplest molecule that one can imagine, but even that is a little bit complex because of the fact that there are 2 electrons. Hydrogen molecule has 2 electrons, and 2 electrons always make things difficult. So, we will imagine an even simpler system which is actually hydrogen molecular ion. We imagine that 1 electron is removed, and this species, which is usually referred to as H2 plus, can be made in the lab and studied. In fact, people have been able to determine the bond lengths, the dissociation energy of the molecule and so on. So, if I think of H2 plus, what will be the Hamiltonian operator? This is our usual style. We always start with the Hamiltonian. So, the system has 3 particles. So, 1, 2, these are the nuclei which I am going to call A and B, and of course, you have 1 electron. So, this is 1 electron, and the distance between the 2 nuclei I am going to call it capital R. Distance of electron from the nucleus A I am going to call it Ra, and this distance naturally will be called Rb. And if you are asked to write the Hamiltonian for the system, how would it look like? Well, strictly speaking, I shall write the detailed Hamiltonian and then argue that some simplifications can be made. You have 3 particles in the system, so all of them will be moving. So, naturally, you would have minus h cross square divided by 2 capital M being the mass of nucleus A, and capital M will be the mass of nucleus B also, because in the case of H2 plus these are 2 protons. So, del A square. Why do I put this subscript A? The reason is simple, because I am concerned with the kinetic energy of nucleus A. And then I have minus h cross square divided by 2 m capital M del B square, where this term represents kinetic energy of nucleus B. Both are moving, I mean in general, of course. And then I have kinetic energy of the electron, which is minus h cross square divided by 2 m del square. Okay. So, these terms represent the kinetic energies, and then in addition to that you have the potential energy. So, what is the potential energy of the system? There are 3 charged particles. So, if you think of the interaction of the electron with the nucleus A, the interaction energy will be minus E square divided by 4 pi epsilon 0 Ra. Electron interacting with nucleus A, then minus E square divided by 4 pi epsilon 0 Rb, interaction of electron with nucleus B, and then there will be the repulsion between the 2 nuclei, which will be represented as E square divided by 4 pi epsilon 0 capital R. This occurs with a positive sign because the interaction is repulsive, while these 2 are attractive interactions, and therefore, you have these negative signs. Now, I had spoken about atomic units in previous lectures. So, we will make use of atomic units because they are very nice and convenient. So, in atomic units what happens is that you will have H cross becoming unity. If you work with atomic units, the value of H cross will be unity. M is the mass of the electron, right. This small m is the mass of the electron. So, what will happen to m? It will be unity, and atomic units are such that 4 pi epsilon 0 also becomes 1. Right. So, my mass of the electron is taken as your unit of mass. So, what will happen to capital M? Well, you see, a proton is 1800 and roughly 40 times heavier than the electron. So, if you measure the mass of the particle, so the mass of the proton in terms of the mass of the electron, it will be about 1800 well, it is 838. So, anyway, let me just write it as how much? 37. So, 1837. So, what will happen to the Hamiltonian if I did these things? H cross will become unity. So, therefore, this term is 1. And so, I will put a 1 there. This capital M will become 1837, and this will become 1, and again that capital M will become 1837. Then again this H cross square by 2m, it becomes 1 by 2. Then this also simplifies, 4 pi epsilon 0 becomes 1, and I should also tell you that in addition to this, you see, you measure charge in terms of the charge of the electron. So, therefore, E also becomes 1. So, therefore, this term simply becomes minus 1 by R A, and this term becomes minus 1 by R B, and that becomes plus 1 by capital R. And you will see that this is very nice, because you do not have to worry about any constants. I mean, they are all unity. Okay. That is a nice thing about this Hamiltonian, and this is actually expressed in atomic units. This is Hamiltonian in atomic units. So, if you find the energy again is going to, the answer that you are going to get will be in atomic units. And one atomic unit of energy, remember, in the case of the hydrogen atom, the answer, if you solve the Schrodinger equation and if you found the energy of the system, you in atomic units you will get an answer of minus half. That is the answer in atomic units, and in the energy of a hydrogen atom, as you would know, is minus 13.6 electron volts. So, minus half is 13.6. So, one atomic unit of energy is 27.2 electron volts. And this is convenient, because once I get the energy, I just need to multiply by 27.2, I shall get the answer in electron volts. Okay. And also in atomic units, the A0, the radius of the first Bohr orbit, is unity in atomic units, but in normal hour units, what will normal units, it is going to be 0.52917 angstroms, which is actually 0.52917 into 10 to the power of minus 10 meters, right. So, remember that when if I calculate the internuclear distance, then I shall get the answer in atomic units, but that can be converted into angstroms. So, using this. So, with this information, let us go ahead and look at this Hamiltonian. But this Hamiltonian, as it is written, it involves 3 particles, it has 3 particles. So, you have differentiation with respect to coordinates of the first, second and the third particle. So, 9 variables are there, very difficult. I mean, this is almost impossible to solve. I should not say almost, it is impossible to solve. Okay. But then if you look at this, you see I did this on purpose. If you look at this term, over that term there is this 1 by 2 into 1837, whereas here there is only 1 by 2. Why do you have 1837? Simply because your nucleus is much more heavier than the electron. This also means that nucleus would be sluggish. I mean, you know that heavy objects move only slowly, so therefore the movement of the nuclei is going to be rather slow in comparison with the movement of the electron. So by the time the nuclei have moved a little bit, the electron would have gone around it several times, which essentially means that electrons are able to, in general, electrons are able to adjust to the instantaneous positions of the nuclei. So if the nuclei have moved a little bit, by the time the electron has already adjusted to the new positions of the nuclei, right. So therefore, even if I did a calculation in which nuclei are assumed to be held fixed at a particular distance. Suppose I do a calculation where the nuclei are assumed to be fixed at a particular distance, and then I do another calculation changing the internuclear distance. That means I am actually changing the internuclear distance very slowly, essentially, right. Even such a calculation is very useful, because even if I obtain the electronic wave function using such an approximate calculation, that is a decent approximation for the electronic wave function, because motion of the electron is actually much faster than that of the nucleus. So this is what I am going to do. What I am going to do is I am going to say, okay, at first I will forget nuclear motion and assume that they are kept fixed at a particular distance. So I will say that, let me say they are kept fixed at a distance of capital R. Imagine they are not moving. If they are not moving, I do not have to worry about these terms, right. That means I am not going to worry about nuclear kinetic energy. So because I am assuming that they are kept fixed. This kind of approximate calculation is actually referred to as the Born-Oppenheimer approximation. But I am not going to describe the mathematics of this, but I have given you the physical idea behind it. Born-Oppenheimer approximation. So what is the approximation? You see, nuclear motion is very slow, and therefore electrons are able to adjust to the instantaneous positions of the nuclei, even when the nuclei are moving. That is essentially what it says. So therefore, what I do is I assume that the two nuclei are kept fixed at a particular distance, and I do an electronic structure calculation. Then I will go on changing the internuclear distance. I repeat the calculation at different internuclear distances, and you may ask, well, what is the use of that? Well, after having done the calculation, what will I obtain? At any particular distance, I am going to get the electronic energy. So I am going to get E, which will be dependent upon that R, right. I am assuming that the nuclei are kept fixed at a particular distance. I find the eigenvalues of this Hamiltonian. This is my Hamiltonian now. So that means I am finding the energy levels of the system, and specifically I am interested in the ground state. And then what I will do is I will imagine that the nuclei are brought from a large distance to a short distance. Then what will happen? The electronic energy of the system will change, and if the electronic energy decreases and reaches a minimum, then I know that there is the formation of a bond, right. I imagine I keep the nuclei at large distance, the system will have some energy, and then if I bring the two nuclei together with one electron, of course, if the energy of the system decreases, then a bond is formed, and if the energy does not decrease, then obviously no bond is formed. So what I would like to have is this E of R, which is the energy of the ground state of the molecule. If I can calculate that and make a plot of it against R I shall take to be along the horizontal axis, E of R will be along the vertical axis, right. And if I made a plot of it, what would I expect? At large separation, what will happen to S2 plus? if I had H2 plus and if I pulled the two species apart, two nuclei apart, what is going to happen? The electron will go with one of the nuclei, and so far away you are going to have a hydrogen atom and a proton, right. If the internuclear distance is very large, you are going to have a proton and a hydrogen atom, and the energy of that system I will take to be equal to 0, which is convenient. I mean, you can take it to have any value if you like, but let me say for convenience the energy of the system when the two species, I mean when the hydrogen and the proton are far apart, the energy of the system is taken as 0, and when I bring the two together, the energy of the system will change, and if it decreases like this, okay, it decreases like this, then I say that there is attraction between the two species, there is attraction, and when you push the two nuclei together, what do you expect? Well, the energy will decrease, let us say, but then at sufficiently close distance the nuclei will repel each other definitely, and therefore, what will happen to this curve? It will turn around and increase. Okay. So, this is what I would roughly speaking expect, this is my expectation, and if this happens, then I can say that okay, that is my equilibrium internuclear distance, which I may denote as R with a subscript E. So, this is a quantity that is that you can measure experimentally, and not only that, suppose you had the molecule with this internuclear distance, then the molecule will have an energy which is that much, and if you supplied from outside that much energy, okay, if you supplied that much energy from outside, then you can cause the internuclear distance to become very large. Let me repeat. Imagine I start with the molecule at the equilibrium internuclear distance, then it will have that much energy, and now suppose you supply energy from the outside, and how much do you supply? You supply that much energy, then you can cause the internuclear distance to become infinitely large. That means you can cause dissociation of the molecule, and therefore, if you calculate this height, then you can get dissociation energy. Which I will denote by the symbol D with a subscript E. So, if you can calculate this curve, what is this curve? This is a plot of the energy of electronic energy of the system as a function of internuclear distance. If I can calculate that, then I can get the equilibrium internuclear distance, I can also get the dissociation energy of the molecule, and therefore, we want to do this, right. So, how will I do that is the question. Let me write the Hamiltonian once again. The Hamiltonian is actually H equal to minus 1 by 2 del square minus 1 by R A minus 1 by R B plus 1 by R. And let me draw this figure once more. I have a one nucleus A here, I have a nucleus B here, and there is one electron. And H of course is an operator. And what is it that I would like to do? I would like to solve the equation H operating upon psi is equal to E psi, okay, and this E will depend upon, E will actually depend upon the separation between the two nuclei, which is what I have already told you. So, therefore, this E is actually a function of R, and I want to know what precisely, I want to know what this function is, because it is very useful. If I knew it, I will be able to find equilibrium internuclear distance, I would also be able to find the dissociation energy of the molecule. So, therefore, this is very useful. Now, this equation is much this Hamiltonian I should say is much simpler than the original actual Hamiltonian. The actual Hamiltonian involved kinetic energy of the nuclei also, but I do not have that in this Hamiltonian, and therefore, this is a much simpler equation, and in fact, it is actually possible to solve it exactly. Okay, the Schrodinger equation for H2 plus with this approximation it can be solved exactly, but we are not going to look at that exact solution simply because you see it is possible to do that only for H2 plus. If you had H2 molecule, then you cannot do it, or if you had some other more complex molecule, you cannot find the exact solution, and therefore, finding the exact solution for H2 plus alone, what is the fun? We want a method which can be applied in general for any molecule that one has. And so, what we do is we use an approximation procedure. In fact, we will use the variation technique. So, how does one proceed? Well, the answer is here. I have to think of a suitable trial wave function phi. Right. For some physical reason, I expect some trial function to be decent trial function, and therefore, I have let me say this phi, and once I have phi, what will I do? Well, I will evaluate something which I have been referring to as script E, which is defined to be d tau integral d tau phi star h phi divided by integral d tau phi star phi. So, this is my variational estimate for the energy of the system. So, I will calculate this, and what is the use of this? This quantity is such that it always is greater than or equal to the ground state energy of the system. Right. This is something the content of the variation theorem, and therefore, I can actually use the variation technique to have an estimate of the ground state energy of the system. So, the question is, what is the variational function that I will use, and that is where physical intuition actually helps. So, let us think about the physical situation. Okay. Now, what would I expect to happen? Well, what I expect is, if I have the two nuclei, right, the single electron, it will be spread. You see, its wave function will be spread throughout the system, and therefore, what I would expect, the wave function may be something like this, it will be spread throughout, something like that. This is what I would expect, and in fact, I am interested in the ground state of the system. That means, if you think of the wave function for the electron, well, it should be spread throughout. Not only it should be spread throughout, I do not expect it to have any nodes. I know that, because this is always the case. When you are in the ground state, the wave function has no nodes. So, therefore, you would expect that the wave function may be spread something like this. Why should it be spread? Because you see the two nuclei are equivalent. So, there is no preferred nuclei with which the electron will go. So, the electron will spend time near both the nuclei. I think I have a picture of that in my PowerPoint presentation. So, this is a pictorial representation of the same thing, but more accurate than what I have drawn there, because you see the different colors are used to show different regions where the densities are different. But now, if this is the way the wave function is, what is the approximate function that I can use? Well, the answer is this one. See, suppose you are thinking of the wave function very close to this nucleus. Suppose you have a point here, and imagine you are very close to this nucleus. If you are very close to that nucleus, well, then you would expect that the influence from this nucleus is much more than the influence from the other nucleus, because the other nucleus is far away. So, in a region that is very close to this nucleus, I can actually take this Hamiltonian and this is nucleus A, right. This is nucleus A and that is nucleus B. So, if you are very close to nucleus A, this 1 by R A is much larger than 1 by R B, and therefore, at least as an approximation I can neglect this if I am confining myself to this region, where the electron is very close to the nucleus. Okay. So, if you can neglect RB, right, if you neglect this term, what does it mean? It means that the electron is predominantly feeling only nucleus A, and if you completely neglected the nucleus B, you have one electron moving in presence of one nucleus. And if you solve the Schrodinger equation, what is the answer that you will get? You will get the answer that the electron is sitting in a 1s atomic orbital, having its center on that nucleus, right. So, therefore, I realize that in the region that is close to this nucleus, the wave function for the electron psi should approximately be resembling a 1s atomic orbital, having its center on nucleus A. So, therefore, I would say that psi has to resemble 1s A. What is 1s A is the question? Well, 1s A is actually 1 by square root of pi A0 cube e to the power of minus r by A0. This is the expression for 1s atomic orbital that we have looked at long ago. But because we are working with atomic units, what will happen? In atomic units A0 is 1, so I can remove this A0 cube, and this is 1. So, therefore, I would have just e to the power of minus r. This is the convenience of working with atomic units. And further, if why do you have this subscript A? This says that you see this is an atomic orbital having its center at nucleus A. And as far as the electron is concerned, now I have to think of the distance of the electron from that nucleus. That is the meaning of saying that the orbital is 1s A. So, therefore, in here you will have e to the power of minus r, but that r is the distance of the electron from the nucleus A, and therefore, you will have to put R A. Okay. So, therefore, you will say that in the region that is very close to nucleus A, psi may be approximated as 1s A, which is actually a shorthand notation. I do not want to write this whole thing, that is why I write that 1s A. But when I write 1s A, it means that I have 1 by square root of pi e to the power of minus R A, where R A is the distance of the electron from the nucleus. Similarly, if you are thinking of the region very close to nucleus B, suppose you think of a point somewhere here, what should be the expression for psi? Psi should be same kind of argument, psi should resemble what? In that region, in this region, psi should be approximately 1s B, where 1s B is an atomic orbital having its center on nucleus B, and its functional form will be 1 by square root of pi e to the power of minus R B. Okay. So, therefore, you can physically argue that near nucleus A the function should resemble 1s A, while near nucleus B the function should resemble 1s B, and therefore, what would be a suitable approximation for the entire wave function? It is clear that I can say, well, a trial function of the form phi equal to some Ca into 1s A plus Cb into 1s B may be a suitable approximation. Why do I say that? Well, in the region that is close to nucleus A, R A is small, and therefore 1s A will have a large value. R B is large, and therefore 1s B will have a small value, and therefore in the region that is close to nucleus A I can neglect the second term. while if you are thinking of regions close to nucleus B, then you can neglect the first term. So, in the region that is close to nucleus A, the function will resemble 1 as A, and in the region that is close to nucleus B, the function will resemble 1 as B, and therefore, I expect that this is a decent, reasonable approximation for the wave function. Now, this technique that I am using is usually referred to as linear combination of atomic orbitals. Why the name? The answer is actually simple. These two are atomic orbitals, and I am combining them after multiplication with some constants. Ca and Cb are constants which I would like to determine, but they are constants. So, you take 1 as A multiplied by Ca, you take 1 as B multiplied by Cb and add. So, you are linearly combining them. After multiplying with some constants, you are just adding them up, and that is why this is referred to as linear combination of atomic orbitals, and for short people would say LCAO, linear combination. So, this technique is referred to as LCAO technique. But then you have the next question, how will you determine the coefficients Ca and Cb? Answer is actually extremely simple. What you will do is you will evaluate script E using this approximate function. Okay, you will evaluate script E using this approximate function, and what will happen? The script E, once you evaluate, it is going to depend upon. See, if this is my trial function, the trial function depends upon Ca and Cb. So, naturally, when you evaluate script E, it is going to depend upon Ca and Cb. So, this script E is going to be a function of Ca and Cb, right, if you evaluate it. The definition of script E is actually here. It is written here. So, phi is a function of Ca and Cb. So, naturally, script E will be dependent upon Ca and Cb. Now, our variation theorem says that for any value of Ca and Cb, this is greater than or equal to the actual ground state energy of the system. That is what it says, the variation theorem. So, therefore, what will I do? I will do the following. I will adjust Ca and Cb in such a fashion that script E has the least value, because even that least value will be actually greater than or perhaps equal to the ground state energy, and therefore, if I found the minimum of script E, the minimum value for script E, even that will be greater than the actual ground state energy. So, therefore, what do? I first evaluate script E and then adjust the coefficients Ca and Cb such that script E has the least value. So, that is my procedure. So, that actually means if I know this function, what I will have to do is I will have to take its derivative with respect to Ca. Why do I have to take the derivative? Because I am looking for the minimum value of this script E. So, how do you find the minimum? You will put dou E by dou Ca equal to 0, and you will put dou E by dou Cb equal to 0. Okay, let us look at these slides for a second. So, here what I am saying is that the wave function actually resembles, in this region the wave function resembles, okay, 1 as A, while there it resembles 1 as B. and so you take a linear combination of the form phi equal to Ca 1 as A plus Cb 1 as B, and now I have to calculate script E. Okay, the expression for script E is already written there, but I will do the calculation and convince you that this is the expression. So how do I do the calculation? The answer is very simple. I have script E, which is equal to integral d2 phi star h phi divided by integral d2 phi star phi. So, this is the expression for script E. Now, let me first calculate the numerator. What is the numerator? Numerator is actually this object. Okay. So, you will have d2, let me write the h here. H is going to operate upon this linear combination Ca 1 as A plus Cb 1 as B, and after that operation is performed, you have to multiply it by Ca 1 as A plus Cb 1 as B with the star. Right, this is your numerator. But if you look at this object, you see you have this star operation can be taken inside, you will have the complex conjugate of Ca, you will also have the complex conjugate of 1 as A. Similarly, you will have the complex conjugates of all these things. We will make a simplifying assumption, which would be that Ca and Cb may be thought to be real, so that the star operation has no effect. And 1 as A and 1 as B, the expressions are already written here. Right, the expressions are written here, you will see that they are already real. So, there is no square root of minus 1 anywhere, and therefore, complex conjugation has no effect on 1 as A or 1 as B. And if I, for simplicity, if I assume that Ca and Cb are real, then this star has absolutely no effect on this function. This is not absolutely necessary, but it is very convenient. Now, what about this this object? Well, you have two terms here and you have two terms there, and you of course have an h sandwiched in the middle, but if you have two terms here and two terms there, when you multiply things out, you would expect 4 terms. So, I will write these 4 terms separately. So, the first term will be integral d2, I would have Ca 1 as A, H Ca 1 as A. How do I get that? This is one of the 4 terms, there are 4 separate terms. So, what you do is you take this and you imagine this H, and this H goes and operates upon that, then you are going to get this term, right. And now you see Ca is just a parameter, it does not depend upon the position of the electron. What is the position dependent term? The 1 as A will depend upon the position of the electron. So, Ca does not depend upon the position of the electron, it is just a parameter, or I can say it is a constant. So, this H, of course, it involves differentiation with respect to coordinates of the electron, but this H would not have any effect on Ca, which is just a constant. So, I can move this from there, it will become a Ca square. But if you are integrating over the entire space, that integration is done over the position of the electron. There again Ca square is a constant, so we can take it out. It is completely unaffected by the process of integration. So, that is only one of the terms, plus you have other terms. In an exactly similar fashion, you will have a term which will involve Cb square integral d2, right. That will be obtained by combining this, that and that, and what will it be? It will be 1 as B, H, 1 as B, correct. And then you will have a term where you have Ca into Cb, this is what I shall refer to as a cross term. Why is it a cross term? Because what happens is that you have this term combining with H and combining with that. So, what will it be? It is going to be equal to integral d2, 1 is A, H, 1 is B, right, and then you will have a term which I will write CB, CA, integral d2. Well, here it is a 1 s B is coming from the right, from the right, and 1 s A is coming from the left. Now, what you can happen is that the reverse thing. So, 1 s B from the left and 1 s A from the right. So, you get that. So, these are the 4 terms that you get. Now, these 4 terms are actually tedious to write. You have to keep on writing them again and again and again. So, what you do is you adopt a shorthand notation. What would be an appropriate shorthand notation? Well, this whole thing. What is it? You have 1 s A operated upon by H, multiplied by 1 s A, and then multiplied by d2 integrated over the entire space. It is usual to adopt a shorthand notation where you say that this object is H A, very convenient notation. And if you adopted that kind of notation, well, there is this term. What will be the notation for that term? HBB. So, that is going to be called HBB. Then you have this term, and naturally you will call this term HAB. Well, notice that I put A on the left side with respect to B. That is because you see on the left side you have 1 s A and on the right side you have 1 s B. And so, naturally this term will be denoted as HBA, right, and therefore, this whole expression I can modify or I can rewrite in this notation. So, it will turn out to be CA square HAA plus CB square HBB plus CACB HAB plus CBCA HBA, that is all, right. And straight away I can make one more simplification. Okay. I am going to claim that HAB is equal to HBA. This is a claim which I will prove. Now, how do I prove this? Well, I know that H, the Hamiltonian operator, is a Hermitian operator. Okay. What is the meaning of saying that? The meaning is that if I had any 2 acceptable functions, what notation shall I use for acceptable functions? Maybe chi1 and chi2. Okay. I take chi2, allow S to operate upon it, multiply it by chi1 star, integrate over the entire space. Okay. Remember the definition of a Hermitian operator: allow chi2 to be operated upon by H, then multiply it by chi1 star and d2, integrate over the entire space. You are going to get an answer, and some number as the answer, because you have integrated over the entire space. So, for a Hermitian operator, what will happen is that instead of doing this, you allow S to operate upon chi1 first and then multiply the result by chi2 star d2 and integrate over the entire space. You will get another number, but for a Hermitian operator, the second number will be the complex conjugate of the first number. That is the definition of a Hermitian operator. For any acceptable chi1 and chi2, the Hermitian operator will satisfy this result. So, if that is the way it is, imagine I take chi1 to be 1 s A and chi2 to be 1 s B, suppose. Then what would I have in between? I would have H and the star I will have to put ditto, right. If I identify chi 1 with 1 as A and chi 2 with 1 as B, the left hand side will be that much. And what about the right hand side? The right hand side will be integral d2 1 as B star H 1 as A, the whole thing star, correct. But then of course, I remember that 1 as A is completely real. So, star has no effect on it. So, I can remove this star, okay. And here again 1 as B is completely real. So, this star has no effect. And if you look at this term, you see everything in here 1 as A, H, 1 as B, they are all real. So, this star also has no effect. And therefore, what is the result that I have obtained? The left hand side is in my notation HAB, and what is the right hand side? The right hand side in my notation is HBA. So, the fact that H is the Hamiltonian operator is a Hermitian operator implies that HAB must be equal to HBA. You do not have to actually evaluate them separately. It is enough if you evaluated one of them, because then it is equal to the other. So, therefore, here this term and that term, if you think about it, they are both the same, and therefore, you can say, well, I will remove one of them, maybe I will remove this one, but then naturally I will have to put a 2 here. So, this is the numerator, and it is exactly that numerator that is sitting in this expression for the quantity script E that appears on the slide, right. You see that this is just what I have now shown. Now, what about the denominator? Okay, in the denominator you do not have this H, that is all. What you have is integral phi star phi d2 integrated over the entire space. So, that will be equal to integral d2 Ca into 1 as A plus Cb into 1 as B, right. Strictly speaking, I should say star, but that star has no effect on this function. So, it is the function itself, and you have exactly the same term. So, what I can do is I can put a square here. Why should I write the other term? Right. It is just a square integrated over the entire space. Now, if you evaluated this by taking the square, what is going to happen is the first term will be Ca square 1 as A square d2, okay. That will be the first term when you evaluate this after taking the square. But in here what will happen, you can take this Ca square outside the integral sign. So, therefore, I can write this as Ca square integral 1 d2 1 as A square plus Cb square integral d2 1 as B square plus, when you take the square, you will get a term like 2 Ca Cb multiplied by 1 as A 1 as B d2 integrated over the entire space. So, these are the 3 terms that you will get, but then you see what is 1 as A square? 1 as A square is the electron density of the atomic orbital. If you integrate it over the entire space, that is going to be equal to unity. So, this is actually equal to 1, because my atomic orbital is normalized, and this integral also in an exactly similar fashion it is normalized, and therefore, this is 1. But this integral is not equal to 1, it is not 0 also, and it is actually referred to as the overlap integral and denoted by the symbol S. So, then what will happen, this object actually works out to be, let me just remove this and write the result. The result is actually Ca square plus Cb square plus 2 Ca Cb into S. This is the denominator, and that is precisely the denominator that that occurs in this equation, and therefore, I have now proved that this expression for script E is correct. And now, what is the next step? This is now a function of C A and C B. The script E as it is written in the slide is a function of C A as well as C B. And so, what should I do? I will have to find the values of C A and C B such that this function has the least value, and that is what I will do in the next lecture. Thank you for listening.